Hello, I am glad to present our work entitled Thermodynamic Modeling and Multi-Objective Optimization of an Alpha-type Stirling Engine based on ideal adiabatic model and evolutionary algorithm. And before start, pose the following plan. We have at first a small introduction. Thereafter, we present the theoretical model used to extract our results, and then the main conclusion. Stocks of fossil fuel in the world are unsustainable. To deal with this difficulty, we should employ renewable energy for power production instead of using fossil fuels. The present work is focusing on Stirling Engine for electricity production in Moroccan remote areas based on solar energy. The novelty of this research is the modeling of an alpha-type Stirling engine and the use of genetic algorithms for multi-objective optimization, knowing that the literature is focusing on modeling only beta and gamma types Stirling engine is a special thermal motor thanks to its capability to operate with external combustion given the opportunity of using renewable energies. It was invented by the Scottish engineer Robert Stirling in 1816. The Stirling engine works according to Stirling cycle, which consists of 4 thermodynamic processes. Firstly, we have the compression of the working gas, then the warm-up of the gas followed by the expansion and the cooling of the working gas. Stirling engine has numerous advantages, making it more suitable to use in comparison with internal combustion engine. The theoretical model used in this work is the ideal adiabatic model developed by Early and Bershowitz. It consists on the division of the engine into 5 control volumes, including the heater, cooler, regenerator, compression space, and expansion space. Adiabatic model is based on the assumptions that the gas temperatures inside the heater and the cooler are constant. To validate the mathematical model used in the present study, we had compared our results with the experimental data of GPU Stirling engine developed by NASA Lewis Research Center. It was found that our model is accurate and validated with experimental results. And geometrical specifications used in the initial design of Stirling engine used in the present research are summarized in this table. The analysis of this study shows the pressure volume diagram during an engine cycle at 1400 rounds per minute. We can see that the expansion work is larger than the compression work. Consequently, the output power will increase. The effect of hot temperature on the efficiency is depicted in this figure. It can be seen that the engine performance increases almost linearly with the heater temperature and reaches the optimal value of 64.86% at 1000 Kelvin. Theoretically, this rise is due to the Carnot efficiency equation, which indicates that the increase of heater temperature can improve the performances of Stirling engine, including the power and efficiency. The graph represents the effect of rotation speed on engine output power at various working fluid. There is a clear trend of increasing in performance for the 3 gases due to the repetition of the pressure-volume cycle. Stirling device can operate at high performance when charged with hydrogen than with other gases at the same rotation speed because hydrogen possesses higher thermal conductivity and low viscosity, followed by helium. In order to be sure of the new Stirling engine design, we have performed a multi-objective optimization, including the output power and efficiency using genetic algorithm, and we had obtained the optimal Pareto front for 2 objective functions. In study, a thermodynamic modeling of an alpha-type Stirling engine was conducted using the ideal adiabatic model for electricity production in Moroccan remote areas based on converting solar energy. Firstly, a sensitivity analysis was carried out using MATLAB software, and then a multi-objective optimization of output power and efficiency was carried out using genetic algorithm. The results show that there is an important improvement in output power and efficiency with the new Alpha Stirling, and thank you for your attention.